All right, everyone, welcome to the first content video for this course. We're going to be covering all of Chapter 1. It's only 3 sections, and I think you've probably seen this stuff before, so I should be able to keep it brief. Don't forget to stick around to the end, though, where we'll share some bonus mathematics that most of you have definitely not seen before. Anyway, let's jump in. We're talking about indices, perhaps better known to you as exponents. So indices tends to be more popular in British English, exponents in American English. Anyway, we know that exponentiation is just the process of repeated multiplication of the same number. So when we have 5 times itself 3 times, we write that as 5 to the power of 3 or 5 cubed. 5 is the base, so that's the number kind of on the bottom, and then 3, we can either call that the index or the power, the exponent, whatever you want to say. So a to the power of n is the same thing as a times itself. How many times? N times. Or we can say that there are n factors of a in that expression. One popular application of this found in computer security has to do with finding the prime factorization of large numbers. So that's just rewriting a large number, a large composite number, as a product of its prime factors. So for example, 144, we can work out that that's equal to 2 to the 4th times 3 squared. And we can do that just by dividing out prime numbers as they come to us. So 144, we start off by dividing that by 2, and that leaves us with 72. Then we divide that by 2, that gives us 36. We divide that by 2, that gives us 18. We divide that by 2, that gives us 9. That's all the 2's. We divide 9 by 3, we get 3. And so there's no more prime factors to divide out. If you've got a larger number, like here, 4,312, just divide out all of your 2's, then all of your 3's, then all of your 5's, then all of your 7's, and so on. I'll give you a moment to try this one on your own, so pause the video, because here comes the answer. There it is. Of course, that requires that you know what your prime numbers are, so here's a list of the first bunch of them generated by the Online Encyclopedia of Integer Sequences, which is a website that I enjoy perhaps more than you would think I should. But that being said, prime factorization is not going to be a major focus for us. So let's jump into some exponent rules here. First, I just want to point out that if we have a negative base and we raise it to an odd power, the answer is always going to be negative. Where it's a negative base raised to an even power is always going to be positive. So like when we square a negative number, it becomes a positive. And since we know that's the case, let's just take a moment and make sure that we know 2 important things about how our calculator functions. First of all, if I want to write down a negative number, I do not wish to use this negative button right here next to the addition, because right away when I press that, it gives me ANS minus. ANS means answer, so what the calculator is trying to do right now, if I were to type 2, is it's saying your previous answer minus 2. But the thing is, I don't even have a previous answer because I just turned the calculator on, so it doesn't know what I want to do. Instead, if I want to get the number negative 2, I want to use this negative sign right here next to the decimal point, and then there's our number, negative 2. I know, to you and I, human beings, the symbols look the same, but on the calculator, they're different. In fact, they look different because when you see them next to each other, the negative sign symbol is like a little bit shorter and it's a little higher up than the subtraction symbol. So calculator is not as smart as a human being, and we gotta, play by the calculator's rules. Anyway, if I want to square the number negative 2, squaring we can do really quickly right here next to the 4. I press that, and this is going to be negative 2 squared, which is, wait a second, we said that a negative number to a raised to an even power should be positive. Well, the calculator follows orders of operations, right? So what we just did is negative 2 squared. 2 squared is 4, and then we made it negative. If we want to do negative 2 and then square that, we got to use parentheses. And there we go. And I'm sorry if you already knew that, but you'd be surprised how many people ask me these questions every year. Last thing, if I want to use a different exponent, so not to the power of 2, I can just use this button right next to the x squared button, and then I can enter in any exponent that I want. And hey, remember this number, it's going to be an answer in just a couple of minutes. But for now, let's head back to the exponent rules. Again, I think you've probably seen these before. So the first 2 kind of go together, right? When we multiply two numbers with the same base, we add the exponents together, but we keep the base. And when we divide two numbers with the same base, we subtract the exponents. So you can kind of see how those two work together, right? The next one, when we raise a power to another power, that means we just multiply the two exponents together. That seems simple enough for right now, but later on in this course, there's going to come times where we're going to need to recognize, hey, we've got x to the sixth in this problem. It would make it a lot easier if we rewrote that as x squared cubed, or perhaps x cubed squared, because all three of those expressions are equivalent, but depending on what we're doing, one might be a lot easier to work with than the others. All right, next two rules also go together. If we're multiplying two numbers together and then raising them to an exponent, or if we're dividing one number by another and then raising to an exponent, basically the exponent just attaches itself to both of the numbers. You can kind of think of it as distributing the exponent, although that's not mathematically correct to say, but I would understand what you meant if you did say that to me. Next we have my favorite one. If we raise a base to the power of 0, we get 1, as long as the base itself is not 0. 0 to the power of 0 is a curious thing, because if we ask our calculator, it will tell us that it is undefined, and I am generally inclined to agree with that. However, if we ask Google, it actually tells us that 0 to the power of 0 is equal to 1. So we'll go to Wikipedia for the tiebreak, and we see here that the most common possibilities are 1 or leaving it undefined. In certain branches of mathematics, we generally want to consider it to be 1, whereas in others we wish for it to be undefined. Unfortunately, the rest of this article is pretty dense and definitely beyond what you're likely to understand at this point in your mathematical lives, unfortunately, so we're going to stop it there. We will agree that 0 to the power of 0 is undefined. Last one down here, if we have a negative exponent, that just means it's 1 divided by the positive exponent. It's the reciprocal of what we originally had. So if we had something like a over b to the negative n, we can rewrite that as b over a to the positive n, because b over a is the same thing as 1 over a over b. I'm going to give you one more rule now, though, that's not in our textbook, and it is what happens when we have a to the power of x over y. So what we do when we have an exponent that is a quotient is we're going to rewrite this as a to the power of x, so that's the numerator of our original exponent, and then we're going to take the y-th, I just said the y-th, the y-th root. So that's like math jargon for not the 5th root, not the 6th root, not the 7th root, but the y-th root. So, for example, you know, if I had, I don't know, say 4 to the power of 3 over 2. So that's the same thing as the square root. I could write the 2 there if I want to, of 4 cubed. Now 4 cubed is 64, and the square root of 64 is just 8. So that's one way to simplify that. Or it might actually be easier to think of this as the square root of 4 all cubed. The square root of 4 is 2, and 2 cubed is also 8. So the order that you do it doesn't even matter. Later on in the course, we will discuss what to do when that denominator is not a 2. So some of you may have seen already in a math course what a cube root is, or a 4th root. Some of you haven't. We're not going to touch it today, but it's coming later on. So for now, if you see a 2 in a denominator, in an exponent, it means to take the square root, and I think you should know what those are about. Now I'm going to spend just a moment explaining why some of those rules work the way that they do. I don't think that this is terribly exciting stuff, so if you really want to skip ahead, you can fast forward to whatever time future me puts in that circle. and then we'll be ready to continue onwards with the content here. So, so for example, why is it that we add exponents together? That seems pretty arbitrary. Why is it that x squared multiplied by x to the fourth should equal x to the sixth? Well, if you just think about it, x squared, what is that? That's x times x, and then x to the fourth, what is that? But x times x times x times x. And look, how many x's are we multiplying together? There's 6 of them. So that's why that rule works the way that it does. And likewise, when we have, say, x squared divided by x to the fourth, we can think of that as x times x divided by x times x times x times x. And then some of those x's will cancel out. And what's left over is nothing in the numerator. Of course, when we're canceling with fractions and there's nothing left, it's a 1. And in the denominator, we have x squared. Now, 2 minus 4 is -2, right? And that's exactly what we have here. We have x to the power of -2. And you can also see with some simple examples why we should multiply those two exponents together. And you can also work out why when we have a product or a quotient all raised to a particular power, that power should apply to both values in the product or quotient. We can also see why a base to a power of 0 should equal 1. Let's take 3's, for example. So usually we think about exponents as repeated multiplication. So 3 to the power of 1 is simply 3, and then 3 squared is 9, 3 cubed is 27, 3 to the fourth is 81, and so on. So as I'm moving along to the right, I'm always multiplying by 3. But if we reverse this process and move to the left, then we're dividing by 3 every time. And we see that when we divide 3 by 3, we get an answer of 1. And so that should be 3 to the power of 0, and that would be true no matter what the original base was. You can start this process with any number that you want, except for 0. Why? Because we can't divide by 0. Calculator doesn't know what it means, and that's because it's not a number, so please don't try to do that. Okay, so let's just look at a few simple examples here. The first one, we have x to the fifth times x cubed. In our heads, 5 plus 3, it's 8. There's no need to show this step, please. Just jump right there. Next one, 6 minus 2, 4. Just answer, done. 2 times 3 is 6. It's y to the sixth. Awesome, this stuff's easy. Let's do a little more. Simplest form with a prime number base. Okay, so 9 to the power of 4. Well, 9 is the same thing as 3 squared. So we really have 3 squared to the power of 4, and 2 times 4 is 8. So 3 to the power of 8 is our answer. So next one, we have 4 times 2 to the p, but 4 is 2 to the 2. So that means we have 2 to the 2 times 2 to the p, and then we can add those exponents together to get 2 to the 2 plus p. Third one, 9 again is 3 squared. So we have 3 to the x over 3 to the 2 all to the y. Let's write that down. Okay, that's what I just said out loud. And then that bottom one becomes just 3 to the 2y. And then subtracting, we get 3 to the x minus 2y. Awesome. And last one, 25 is 5 squared. So we've got 5 squared all to the x minus 1. So we distribute to get 5 to the 2x minus 2. How much fun was that? Let's continue. So I didn't, whatever, we don't need to hide the answers here. So anything to the power of 0, as long as it's not 0, is 1. Done. 3 to the negative 2 is the same thing as 1 over 3 to the positive 2, which is the same thing as 1 over 9. Amazing. We have 3 to the power of 0, which is just 1, minus 3 to the power of negative 1, which is the same as 1 over 3 to the 1, or 1/3. So we have 1 minus 1/3. That's 2/3. And finally, 5/3 to the negative 2 is the same thing as 3/5 to the positive 2. And then we square both of those numbers to get 9/25. Here are some slightly tougher examples that are not found in our textbook. So when we've got multiple variables going on, or in both of these cases, multiple variables and constants, I encourage you to just do them one at a time. So this first one, I would ignore the a and the b, and I'd just think, hey, I got 3. 3 is in parentheses. It's raised to the power of 4. What's 3 to the power of 4? 81. Okay, so I know that my answer is going to have an 81 in it. Then I would think about the a. I've got a cubed. A cubed to the power of 4. So that means I'm going to multiply 3 by 4 to get a to the 12th. Finally, I have b to the power of 4. There's nothing else to say about that. It's b to the power of 4. That's it. You can do all of that in your head. There's no reason to be overwhelmed by it. Just do them one piece at a time. Same thing with the second one. We have x squared cubed, okay? So I'll have x to the 6th in my numerator. In my denominator, then, we're going to have 2 cubed, which is 8, and then y cubed. All right, so now we're into section C, scientific notation. Not a major focus for our course, but it does have one application for us, and it's likely to show up in your science classes, so let's just discuss it really quickly. A number is in scientific notation if it is in this form right here, where a is some number in between 1 and 10. It could be equal to 1. It must be less than 10. And then we multiply that number by 10 to the power of k, where k is just some integer value. So this is a way of taking numbers that would normally be very long and kind of shortening them down a little bit. This is why it's called scientific notation, because when you really get into a lot of science fields, like for example, if you're doing astrophysics, you're going to deal with distances that are enormous. Or if you're doing like particle physics, you'll deal with objects with incredibly small masses. And so rather than have to type out 20 zeros in a number that you're working with, scientific notation makes it a little bit easier to write down and to fit on a page. So anyway, first example here, we've got, what is it, 23,600,000. So first I look for, you know, the part that's not involved with the zeros, which is that right there. I want to find a number that's going to be in between 1 and 10, so I'm seeing 2.36. All right, that should be easy to identify, and then we just ask ourselves, how many places do we need to move the decimal point? That decimal point right there, we need to move it 7 places to the right to get the original number, so we're going to multiply 2.36 by 10.7. In our second example, we have a very small number. Again, it's 2.36, right? We see that right there. But in this case, that decimal point needs to move 5 places to the left to get that original number. So it's 2.36 times 10 to the negative 5. We can also start in scientific notation and do it the other way. So here we're going to do 2.57, but we're moving the decimal point 4 places to the right, giving us 25,700. Here we're going to move that decimal point 3 places to the left, so we got 0.007853. All right, so we should feel comfortable going between scientific notation and standard notation in either direction. Great. Here, just slightly more complicated ones. Can we write either of these in scientific notation? Yes. And we're going to do it kind of like we would have done it with variables. This helped me out when I was in school because I didn't like scientific notation. But I realized that if I thought of this as 3x to the 4th multiplied by 8x cubed, then I knew exactly what to do. When I multiply those two numbers together, I know I get 24 times x to the power of 7. Well, guess what the answer to this problem is? It's going to be, well, we could start off by thinking of it as 24 times 10 to the power of 7, because we're just replacing the 10s with x's, but then that's not proper scientific notation because 24 is too large, so I'm going to rewrite that as 2.4 times 10 to the power of 8. And we can do the same thing here. We don't even need x's though, so we're still going to have 2 divided by 5. Actually, let's change that to a decimal right now. 2.5 is, 2 over 5 rather, is 0.4. And then we're going to have 0.4 times 10 to the power of, well, negative 3 minus negative 8. That's the 5th. Problem, 0.4 is not in between 1 and 10. So we're going to need to make it just a little bit bigger here. So because we made the 0.4 larger, we're going to make the 10 to the 5th a little bit smaller. So it's going to be times 10 to the power of 4. If you're working with your calculator, Calculator doesn't give answers in scientific notation. It does give answers with this capital E. That means scientific notation. Okay, so this really says 1.25 times 10 to the power of negative 10. So if you ever get a number on your calculator that looks like that, that's what it means. What's the last digit of 3 to the power of 23? Now, we already saw that answer earlier, and I believe it was a 7. But we can work this out without a calculator if we just think in terms of patterns. So a lot of the times in mathematics, when we have a hard problem, a good problem-solving technique is to begin with easy stuff that we know and then to search for patterns and see if we can figure something out from there. So let's think about some powers of 3 that we know. 3 to the 0 is 1, then we've got 3, 9, 27. We wrote these down earlier, 81, 243, and so on. What we're interested in this problem, though, is just the last digit. So let's just focus on those. 1, 3, 9, 7, 1, 3. I wonder if a pattern is emerging. So 3 to the power of 6 is going to be 729. Yes, that has a 9 as its last digit. And 3 to the power of 7, its last digit is going to be 7. So we have this repeated pattern, 1397, 1397. The question is, where does 3 to the power of 23 fall into that? And we could just, write out this pattern a whole bunch of times and start counting, but there's actually a faster way to do it. And I'm pointing this out because this will show up a few more times before your high school mathematics career is done, like using the trick I'm about to employ. So since it's a pattern of 4 numbers, all we need to do is divide 23 by 4 and then see what its remainder is. So 23 divided by 4, we get 5 with a remainder of 3. So that means that our answer is going to have the same final digit as 3 to the power of 3. Any exponent that we could have had up here, if it had a remainder of 0, which would mean that it was exactly divisible by 4, then it would have a last digit of 1. If it had a remainder of 1, it would have the same last digit as 3 to the 1. Remainder 2, have the same last digit as 3 to the 2, and remainder 3, same last digit as 3 to the 3. If it had a remainder of 4, well, it wouldn't have a remainder of 4, because if we're dividing by 4, we can't have a remainder of 4, can we? Now, the real mathematicians watching this video will point out, hey, wait a second, how do we actually know that this pattern continues? Just because we see a few instances of it doesn't mean that it goes on forever. Well, you're right, but in this case it does. I'm not going to prove that here. You'll just have to trust me. Okay, folks, here we go. The bonus mathematics for this video. We've got 3 very basic mathematical operations on screen. You know them all: addition, multiplication, and exponentiation. But as before, I want us to look at these now and think about patterns and consider how we could extend that pattern to the next level. So we begin with addition. If we want to add a plus n, one way to think of that is we're going to add a whole bunch of 1s together. How many 1s? N 1s. Make sure this makes sense to you. If you wanted to add a plus 3, that's the same thing as a plus 1 plus 1 plus 1. There we go. And there are 3 1s there. If I want to do multiplication, a times n, we can think of that as repeated addition. We're going to add a bunch of a's together. How many a's? N a's. Exponentiation is just repeated multiplication. If I have a to the power of n, that's a times a times a times a times a. How many a's? N a's. So we see that exponentiation is just repeated multiplication. Multiplication is just repeated addition. Whenever I see a pattern like this, I like to think, can I extend this in either direction? I don't really think it makes a lot of sense to try to move up that way because I'm not really sure what the next step would be. But it seems as though we should be able to add a new operation down below that would include repeated exponentiation. And indeed we can. So this is something called tetration, which is when we raise a to the power of itself, so a to the power of a to the power of a to the power of a, and so on. How many a's are going to be involved in this little tower here? N of them. And this is pretty wild. This gets us incredibly large numbers very, very fast. The notation we see is just like exponentiation, except the I don't know. I don't want to say exponent. I'm not actually sure what the word is for that. So we'll call it the fake exponent. The fake exponent just goes on the left instead of on the right. So hey, I want to like experiment with this. So let's check this out. So here's a couple of easy examples. We're going to do tetration with a base of 1. So this is really easy because it's always equal to 1, right? So this first one, or I should say, this is going to be 1 tetration 2. 1 tetration 2, that just means we're going to do 1 to the power of 1. So it's a tower of 1s that's 2 in size. There are 2 1s there. Got it? So 1 to the power of 1 is obviously just 1. And then this next one, so this is going to be 1 to the 1 tetration 3. That's just going to be 1 to the 1 to the 1, which is still equal to 1. And then this next one, 1 tetration 4, is 1 to the 1 to the 1 to the 1, which is still 1. You get it. Okay, that one's pretty boring. Let's go one step further down. Oop, changed colors by accident. No problem. With 2's now, we already see some very large numbers over there in the right couple of columns. So this first one is, this is 2 tetration 2. That just means it's a tower of 2's, and there are 2 of them. So it's really the same thing as 2 to the power of 2, which is, of course, 4. 2 tetration 3, oops, 2 tetration 3 is 2 to the 2 to the 2. Now when we do this, we work from right to left, essentially. So the first 2, that's 2 to the power of 2, which we already know is 4. And so then the whole thing becomes 2 to the power of 4, which we know is 16. This next one, 2 tetration 4, that's going to be 2 to the 2 to the 2 to the 2. All right, well, we've already worked out previously the 2 to the 2 to the 2 is 16. So this is really 2 to the power of 16, which you should not know off the top of your head. But 2 to the power of 16 is 65,536. Which is why, in this next one we just have, we see right there, this next one's going to be 2 to the power of 65,536, because that's going to be 2 tetration 5, which is going to be 2 to the 2 to the 2 to the 2 to the 2. And we already know that those 4 2's make 65,536. So these numbers get really big, really, really fast. Here's a few others, and I mean, there's some notation happening over here that you've likely not seen before. Let's not worry about it. I don't know. It's a cool thing, and I thought I would share it with you. All right, that's it. So if you've got a question, or if I said something that was just totally wrong, then please shoot me an email or leave a comment in the video so that I can try to address those. Don't forget to like and subscribe. No, I'm just kidding. There's absolutely no reason to do that for this. Just, you know, hope you enjoyed and learned something. Catch you next time.